Okay. Um, okay, everyone. Welcome again. Good morning, and welcome to this section. And how has it been? Hope we are staying safe in our various homes and places. Please do ensure to stay safe. And I must tell you this that the management of GPT is strongly praying for every one of you for God's protection. Now, welcome to today again. Topic applied physics. And last week we tried to establish the facts, look at some definitions, and we gave some assignments last week. And so many of us did the assignment, turned in, and others did not turn in. Please, I want to let us know this that if you are turning in your assignment, please and please again use the title, the course title, to as the subject of the assignment. Don't just straight there and say assignment. No. Now today, let's go because of the work of loads we have today. I'm not be able to do a recap of what we did last week. Now let's look at wave propagation. Wave propagation. Wave propagation is any of the ways in which waves travel. These are any of the ways in which waves travel with respect to the direction of the oscillation relative to the propagation direction. So in the any direction in which wave travel is wave propagation. Any direction in which wave travel. So if you go to river or you go somewhere, you see the waves, you see the flowing, moving in. So you know waves travel in the direction, travels in direction. And when we talk about wave propagation, we are saying is any of the ways in which wave travel with respect to the direction of the oscillation relative to the propagation direction. We can distinguish between longitudinal wave and transverse waves for electromagnetic waves. So we can tell the differences between a longitudinal wave and a transverse wave. Propagation may occur in vacuum as well as in material medium. Propagation may occur in vacuum as well as in material medium. Other wave types can not propagate through a vacuum and need a transmission medium to exist. Now, other wave type cannot um, propagate through a medium, through a vacuum, sorry, and they need a transmission medium to exist. They need something to amplify them or transmit them before they can exist. Before they can exist. So you can see the diagram we have the respect to it. Now let's look at the types of propagations. There are three types of propagations. We have the ground wave propagation, and we have the sky wave propagation and the space wave propagation. So we have three types of propagations which I just mentioned to you. Now let's look at them, establish a fact around them one after the other. Ground wave propagation is a method of radio frequency propagation that uses the area between the surface of the Earth and the ionosphere for transmission. Ground wave propagation, I said, is a method of radio frequency propagation that uses the area between the surface of the Earth and the ionosphere for transmission. The ground wave propagation is a considerable distance over the Earth's surface, particularly in the low frequency and the medium frequency propagation of the radio. Ground wave radio propagation is used to provide relatively local radio communication. You in your house, you hear the advertising, or sorry, they are transmitting from a small place called a radio station, and you're getting from different corners of the states where you are, or different corners of the locality where you are. Based on ground wave propagation. Ground wave propagation. Now, sky wave propagation talks about or refers to radio wave propagation via the ionosphere. Ionosphere. It talks about ground wave. Thank you. It refers to the radio propagation via the ionosphere. Each reflection from the ionosphere is a hop. Reception of skywave propagation is called skip. The reception of skywave propagation is called skip. Like what most of us will say, the network. Let me use the language that most of us will like get. Is the network of skywave propagation is called skip. But in any way, please just let you know that it's reception. So I just want us to know where and what I'm talking about. That's why I decided to use the network. The signal you get is called skip. It's called skip. The higher the region in the ionosphere where the hub occurs, the greater the distance the wave can travel. The higher the region of the ionosphere, the higher the region where the waves occur, where the hub occur. Now I told you what the hub is. That a reflection from the ionosphere is the hub. So from the higher the reflection from the ionosphere, the greater the distance the wave travel, the greater the distance the wave travels. So we can get that from this. Then the skip can travel up to 2,500 miles. The F2 skip can travel 2,500 miles. The E skip from the diagram I'm talking about, if you can see my diagram very well, I'm trying to tell you that the F2 on my diagram can travel up to 2,500 miles, while the E skip can travel up to 1,200 miles. Skyway propagation multiple hops can include multiple hops between the Earth and the ionosphere. It can include multiple hops or so many hops. So many. So you know when it's more than one or two is multiple. So that is what it's telling us about. Now that brings us to the space wave propagation. The space wave propagation have high frequencies and are basically called space wave. The radio waves having high frequency, and these are also known as space wave. Call them space waves. Space waves are radio waves having high frequencies. They are radio waves having high frequency. These waves have the ability to propagate atmosphere. They have the ability to move through atmosphere from transmitter antenna to receiver antenna. So they have the power, or they have the ability to travel through the atmosphere. That is why you can be sitting in your house right now. Everyone is sitting in his or her house, and I'm in one place just trying to talk about what I'm doing, and we are all hearing us now. There is no connectivity. There is no LAN cable connecting where I am to where you are. So we are just operating on the wireless on a wave. We are just operating. No, in your same thing applies in your radio station. You They are there in one small building, and in one building and in one small room broadcasting, and you are getting it from every corner of the location where or of the state where you reside, and you can tune from one station to another. This is as a result of the ability for the space wave to travel through atmosphere from transmitter antenna to receiver antenna. So now before you can get it, let me try and explain something so that we get it. For you to get the signal from the radio station or the transmitter, they have what we call a transmitter. So when they broadcast that, their broadcast is passed on to the transmitter. The transmitter sends it out, and your antenna, which is called the receiver antenna, receives it into your system, and your system starts listening to the broadcast which is going on. Same thing applies when we talk about the connectivity, network connectivity you are using to browse right now. Now the network provider has their transmitter positioned at so many places in order to cover their particular area. So their transmitter transmits, and via your own receiver on your phone or on your device, you are able to receive their network. And if you subscribe to their data, you get their network and you are able to use their data. So it's also in radio transmission. When they broadcast, it goes to the transmitter, then the transmitter sends it out. So every antenna that is positioned at that angle, the antenna receives it well. The antenna receives it well. So if you look at the next slide on the, you are looking at the screen now, we have range of waves propagation. We have the range of waves propagation. You see them. Then we have the electric field type on the screen also. You see them. Now let's look at electrostatic. We've talked about wave. We've seen how wave operates. So let's look at electrostatic. Electrostatic. When two types of objects are rubbed together, electrons are transferred from one surface to another. When two types of objects are rubbed together, electrons are transferred from one surface to another, causing the object to become charged. The object which gains electron becomes negatively charged, and the object that loses electron gains a positive electron. Now, get what I'm trying to say. In electrostatics, when two objects, take two metals or two objects, rub them together, and when you rub them together, electrons are transferred to from one surface to the other surface, causing objects to become charged, causing the objects to become charged. The objects are now become charged. Then the objects which gain the electron becomes negatively charged, and the object that loses the electron becomes positively charged. So it gives out electrons in order for it to receive electron to be positively charged. So it gives out it if two balloons were charged by rubbing them on a jumper, then huge side by side from a fine thread, what would you expect to happen to the balloons? What will you expect? So those are the things. So you expect that okay, one will be positively charged and one will be negatively charged. No, we already know that these charges repels. So you will just know from this when you bring two of them together, their charges repels and opposite charges attract. So their charges, if they are of the same thing, they repel, but opposite charges or like terms attracts, like what we taught in our physics, like them attract each others. Now, Coulomb conducted an experiment into the force of attraction and repulsion. Coulomb's conducted experiment and where we have the Coulomb's law, and the result he got is called Coulomb's law, and it describes the behavior of charged particles in a similar way to Newton's law explaining the force of gravity between objects. That's Coulomb's law. Coulomb's law. Now, Coulomb's law, let's state it. Coulomb's law states that the magnitude of a force F between two electrically charged bodies, which are small compared to their separations, R1 is inversely proportional to R2 and proportional to the product of their charges Q1 and Q2. Coulomb's law states that the magnitude of a force F between two electrically charged bodies, which are small compared to their separation R, is inversely proportional to R2 or and proportional to the product of their charges Q1 and Q2. You can also say that take it this way, that it is the force. It says that the force between 2 point charging 2 point charge in Q1 and Q2 is directly proportional to the product of their magnitude and inversely proportional to the square of the distance separating them, that is R. So now when you look at the screen, we have F is inversely proportional to Q1 Q2 all over R squared. So that is what Coulomb's law states. F is directly proportional to Q1 Q2 all over R squared. Now what are we saying is that with this formula is telling us that the force between 2 points Q1 and Q2 is directly proportional to the product of their magnitude and inversely proportional to the square of distance between them. So where F is the force, then Q1 and Q2 are the 2 point charges, and R square is the distance separating them. R square is the distance separating them. So we can see our Q1 and Q2. Now look at, if you notice what the diagram I have on the screen, you see that most not you see that you must be paid notice must be paid to the charges of the bodies. Notice must be paid to the charges of the body. Thank you. Paid to the charges of the bodies. The charges may not be the same magnitude or have same polarity. They might not be the same magnitude or have same polarity. It might be positive, one might be positive, or the other might be negative. So they might not necessarily be the same thing. But we when an acid in a constant, then we have, when we go through the formula we just brought, now we get this. When we add in our constant, this becomes F. We don't forget I said F is equal to force. F is equal to force. Thank you. F is equal to force. We are adding the constant 1 all over pi and 4 pi r extension, which is equal to multiplied by Q1 Q2 all over r squared. So from here now we have our force, our F as force, which is in Newton, then our Q1 Q2, and which is the charges, which is capacitance C, and the arrow is the separation, the distance between them, which is n in meters. Then we have the permittivity in farad per meter. Permittivity in farad per meter. So this is it. The permittivity of free space vacuum is given by permittivity naught, and its value is determined by experiments. Its value is determined by experiments. Now let's look at, when we go through this, we now have our C, which is the constant, is equal to 1 all over root mu naught all over H naught. Then the constant will give us, okay, with what we are seeing on the board. Thank you very much. So you see the constant after imputing everything, and this is what we get as our constant. This is what we get as the constant after having the constant. So let's try and look at a problem, solving a problem here. Let's solve a problem with, on the next slide. Problem number 1. It said the average distance r between the electron and the proportion of the hydrogen atom is 5.3 by 10 raised to power minus 11 meters. A. What is the magnitude of the average electrostatic force that acts between these two particles? B. What is the magnitude of average gravitational force that acts between these particles? So if the man on the slide there is there, please kindly move to the next slide and let's see this. Now, when you see from the question, we have our question here, and we said number 1 says what is the average distance? What is the average distance? The average distance, thank you, the average distance between the electron and the proton in the hydrogen atom is 5.3 times 10 raised to power minus 11 meters. Now question number 1 says, what is the magnitude of the average electrostatic force that acts between two particles? B. What is the magnitude of the average gravitational force that acts between these particles? So now let's look at the solution. What I have here, I just the electrostatic force. So from what we have, then F of E is equal to K, which is Q1, Q2 all over R squared. So when we bring it down, when we impute the values, we have 8.99 multiplied by 109 Newton per meter square, then 1.60 multiplied by 10 raised to power minus 19. Sorry, it's 10 raised to power minus 19 all squared. So when you go through this, by the time you do your computation, we have 8.2 times 10 raised to power minus 8 Newton. Please don't forget to always put the unit. The unit is very, very important. The unit is very, very important. So that is what he's saying. We've been able to establish the fact that the electrostatic force is 8.2 times 10 raised to minus 8 Newton. Then the gravitational force, which is the B part of the question, then we have F of G, F subscript G, um, equals G into M1, M2 all over R squared. So when we compute the values, we put in the values, we get 1.91 times 10 raised to power minus 57 Newton. So we could see, please, let's try and note these calculations and let's try and practice them, especially the formulas. It's not what you can cram, just to know them and you'll be able to dish them out whenever you are called upon. Now let's solve another one, question number 2. On the next slide, um let's say question number 2. The nucleus of an iron atom has a radius of about 4 times 10 raised to power minus 15 meters and contains 26 protons. What repulsive electrostatic force acts between two protons in such a nucleus if a distance of one radius separates them? If a distance of one radius separates them. So if you go through the slide, the man on the slide, if you can go to the next slide, now you see that F of E, that is the nucleus of iron, is equal to kq1 q2 all over r squared. So when you put in the values, it will give us 14 Newton. It will give us 14 Newton to give us 14 Newton. So the same applies again when we try to establish a fact. I have another question here, another example we want us to treat. So today let's take on treating examples. I want you to be familiar with the calculations on this. I want you to be familiar with the calculation on this. Now example number 3. Example number 3 says two balloons. Example number 3 says two balloons with charges of plus 3.37 microcapacitance and minus 8.21 microcapacitance attract each other with a force of 0.0626 Newton. Determine the separation distance between the two balloons. Find R. Find R. Now we want to find R. We don't know R. So we now come establishing the value. Okay, Q1 is equal to, trying to get the values. Our Q1 is equal to plus 3.37, so which is equals to 3.37 times 10 raised to power minus 6 capacitance. Then the K is equal to 8.99 times 10 raised to power 9 Newton per meter square. Then the Q2 is equals minus 8.21 microcapacitor or capacitance equal to minus 8.21 times 10 raised to power minus 6 C. So the Fe now is equals minus 0.626 Newton. That is, use a force value since it's attractive. We're using a force value since it is attractive. So when we come, we've known everything. So we come using the formula. Fe now is equal to K Q1 Q2 all over R squared. Now don't forget we are asked to look for R. So how do we do that? So when you do that by uh, cross multiplication, we have R squared is equals K into Q1 Q2 all over F F of E, F subscript E. Then the R squared now is equals K multiplied by Q1 Q2 all over F E. So R now, removing arrow, because we are asked to find arrow, so we now take it to the other side. We have the square root of k into q1 q2 all over f e, f subscript e. So impute the values given. When we impute the values given, we have 1.99 meters. We have 1.99 meters. So when we impute the values given, we have 1.99 meters. So that is what we get in this area. Then let's look at problem number 4. Problem number 4, that is slide 22. Slide 22, problem number 4. Slide 22. Now, three charges on a line. We have three charges on a line. Now determine the magnitude and the direction of the net force on QR. So we have three charges on the line. We have we have Q2 with then Q2 to Q1, that is 0.2 meters, Q1 to Q3 0.15 meters. Then in Q2 we have minus 4.0 microcapacitance. Then Q1 we have plus 3 and Q3 we have minus 7. We have minus 7. So now the B part of it, we have the F sub 12, we have the Q1, and we have the F sub 1, 3, and so on and so forth. Now the B part is free body diagram. So we want to solve this, and I don't know, I pray at the admin should be able to forward these materials to us so that we go through we'll go through them, because I don't know how to forward materials to you right now, because I don't have all the time to start forwarding email by emails. So, and let's go through our solution. If we go through our solution, and we'll be able to like F12 now is equal to K into Q1 Q2 all over R square. So when we impute the values, we all have our F12 as minus 2.7 Newton. And so also in F13, thank you, in F13, we when we impute the values also into the formulas given, and we have F, the force is equals magnitude of the force is F12 plus F3, which is minus 2.7 plus 8.4, and we have plus 5.7. We have plus 5.7. So now we've gotten that, and we know through finding the net force of Q1, we have, if you see the diagram on slide 24, you see that F, we have the formula we use in F is equal to F12 or F subscript 12 sine theta plus F subscript 13 cos theta for the angle. So we impute everything here, and to the next slide, slide 25, we get what is here. We'll be able to get our F subscript 12 as minus 9.59 Newton, then F13 as minus 17.98 Newton. So because we're looking for the F now, F is equal to F12 sine theta plus F13 cos theta. This will now give us 9.59 sine 73 minus 17.98 cos 73, and when we use our calculator, it gives us minus 14.43 Newton. So let's look at slide 27, the electric field strength. The electric field strength, slide 27. Now, an electric field exists in a region of electrical force. In a region of an electric field exists in a region if the electrical forces are exerted on the charged bodies or particles in that region. The direction of electric field at a point its direction is the direction in which a small positive charge would move under the influence of the field if placed at that point. So you can see from the diagram I have here, the next slide, we'll see plus Q, and the other side minus Q, and that's the point charge and the test charge. A point charge gives off a radial electric field similar to planet causing radial gravitational field. Now we can calculate from this the strength of the force experienced by Q using the formula here, using the formula below on slide 28, using the formula below, which gives us force F is equal to 1 all over 4 and Q1 Q prime all over R squared. So this is on the slide there. We can see it from slide 28. Now, the electric field intensity is the force per unit charge. So the electric field strength at Q prime is given by E is equals F all over Q prime. E is equals F all over Q prime. Now, if we substitute 1 into 2, equation 1 into 2, this is equation 2. When we do the substitution, then we have the radial field equation. We have E is equals 1 over 4 pi Q all over R squared. We have the radial field formula. We have that there. Then the electric field strength in a uniform field. The electric field strength in a uniform field. Now, if we consider two parallel conducting plates A and B, a certain distance apart D, from what you can see from my screen, a certain distance apart D, there is a potential difference V between the plates. There is a potential difference between the plate. The field between these plates will be uniform. So the fields between these plates will be uniform. So you can get that from the slide 31, which is on my slide here. So the field is uniform between two plates with all field lines parallel except at the edge. With all the field lines parallel, the field is uniform within the plate except at the edge. There is a potential gradient between A and B. The potential gradient between A and B, if the same at any point, the potential gradient between A and B is the same at any point except at the edge. So the potential um, gradient of the objects are the same except at the edges. The potential at any point is therefore equal to the average potential. The potential at any point is therefore equal to the average potential, the size of which is V all over B. Therefore, the electric field strength E is given by E is equal to V all over D. That is the electric field strength, the formula for the electric field strength. Let's take a few questions on this. Please take this down. I just want you to try it on your own as an assignment. Hydrogen hydrogen single electron orbit about 0.5 amps, that is 5 times 10 raised to power minus 11 meters, from the center of the nucleus. Work out the force acting between the nucleus and the electron. I said hydrogen single electron orbit about 0.5 amps, and that is 5.10 raised to power minus 11 from the center of the nucleus. Now, question 1 is work out the force acting between the nucleus and the electrons. Work out the force acting between the nucleus and the electrons. So if the slide you can go to slide 33. The questions are there. And number 2, B, work out the field strength at the distance R. Work out the field strength at the distance R. Work out the field strength at the distance R. Question number 2, chlorine's outer shell is about 2 times 10 raised to power minus 10 meters from the center of its nucleus. A, work out the force of attraction between the nucleus and an electron in the inner and outer shells. Work out the force of attraction between the nucleus and an electron in the inner and outer shells. B, what is the difference in electric field strength between the two orbits? What is the difference in electric strength between the two orbits? Now, question number 3. The dome of a Van de Graaff generator has charges of 20 capacitance. The dome is 20 centimeter across. Calculate the field strength 1 millimeter above the dome. Calculate the field strength at a distance of 30 cm. 2. I said question number 3. The dome of a Van de Graaff generator has a charge of 20 capacitance 20 C. The dome is 20 cm across. 1 or A, calculate the field strength 1 millimeter above the dome. B. Calculate the field strength at a distance of 30 centimeters. Question C. If a sphere with a negative charge of 3C was placed 15 meters from the dome, how much force would it experience? Question C. If a sphere with a negative charge of 3C was placed 15 centimeter or 15 cm from the dome, how much force would it experience? How much force will it experience? We are on slide 34. How much force will it experience? Thank you. Slide 34. So, and question number 4. An scanning electron microscope accelerates the electrons using plates with holes in them. Assume the plates are parallel and creating a uniform field. The accelerating voltage is 8.5 k. The accelerating voltage is 8.5 kV. The poles are 12 cm. The plates are 12 cm apart. Question A. Calculate the electric field strength. If the accelerating voltage is dropped to 5 kV, what is the field strength? I repeat that question number 4 again because our time is up. I said a scanning electron microscope accelerates the electrons using plates with holes in them. Now assume the plates are parallel. It is on the screen. Assume the plates are parallel and creating a uniform field. The accelerating voltage is 8.5 kV and the plates are 12 cm apart. Question A. Calculate the electric field strength if the accelerating voltage is dropped to 5 kV. And question B. What is the field strength? So please let all your answers, turn all your answers in, send it to safetybliss@yahoo.com. Safetybliss@yahoo.com. I spell again SAFETYBLISS@yahoo.com. Double S for Sunday. So double S@yahoo.com. Safetybliss@yahoo.com. So let's get these assignments to me not later than Tuesday next week, 23:59 p.m. Not later than Tuesday next week, 23:59 p.m. And on your own too, I will advise you please go through this and go through the material. And I think if the management will allow me, I would like to take us to a platform on Dome, but I can't do that except the management authorization where we can solve these things. That you see my templates, you see my whiteboard and the explanation properly. I want to say thank you again for listening, and please don't forget to turn in your answers to safetybliss@yahoo.com. Thank you and God bless you. See you next week.